Namaskar, I am Dan Gaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur, and we come towards Lagrangian formulations. And in Lagrange's formulations from classical mechanics, we study the Lagrange's equation of motions from for like a conservative system, for non-conservative system, for partially conservative and partially non-conservative system. In deriving Lagrange's equation of motion, the requirement of holonomic constraint do not appear until the last step. For conservative system, if the system is conservative, so that the particle moves under the influence of a potential which depend on the coordinate only. Therefore, Fi is equal to minus del I, V is equal to del by V by del by Ri. In this case, the component of the generalized force becomes Qj is equal to dou V by del by V by del by Qj, del by Ri by del by Qj is equal to del by V by del by Qj, and V is not equal to V of Qj dot. Hence equation 12 becomes d by dt of dabba of t minus v by dabba qj dot minus dabba of t minus v of dabba qj is equal to 0, but L is equal to defined. L is equal to t minus v. Therefore, d by dt of dabba L by dabba qj dot minus dabba L by dabba qj is equal to 0 for j is equal to 1, 2, 3 dot n. These are the called Lagrange equation of motions for the conservative holonomic system. The Lagrangian L satisfying equation is not unique for non-conservative system. In case of non-conservative system, the scalar potential U may be functions of both position and velocity. U is equal to U of qj dot t. Such a potential is called a velocity dependent potential. In this case, the associative generalized forces is given by qj is equal to minus del by u by del by qj plus d by dt of del by u by del by qj dot. Substituting in this, d by dt of del by L by del by qj dot minus del by L by del by qj is equal to 0, which are the Lagrange equation for non-conservative system. Next, partially conservative and partially non-conservative system. Consider the system is acted upon by conservative forces Fi and non-conservative forces Fid. Such a situation often occurs when frictional forces or deceptive forces are present in the system. In this case, the component of the generalized forces are given by Qj is equal to Fi plus Fid del by Ri by del by Qj. This implies that Qj is equal to minus del by V by del by Qj plus Qj of d, where the non-conservative forces which are not generalized derived from potential v are represented in qj of d. So substituting this in equation 12, we readily obtain d by dt of del by L by del by qj dot minus del by L by del by qj is equal to qj of d. J is equal to 1, 2, 3 dot, where the Lagrangian L contains the potential of the conservative forces and Qj of d represent the forces not arising from the potential V. However, it is found by experiment in general Fi d is equal to minus lambda Ri dot. Lambda are a constant, hence we have Qj of d is equal to Fi of d del by del by Qj minus lambda Ri dot del by Ri by del by Qj but we know that del by Ri by del by Qj is equal to del by Ri by del by Qj, and therefore Qj of D is equal to del by del by Qj dot minus 1 by 2 lambda Ri dot square is equal to minus del by del by Qj, where R, capital R, is equal to 1 by 2 summation of lambda Ri dot square is called release deception function. Hence, the Lagrange equation of motion for a non-conservative and partially conservative system d by dt of del by L by del by Qj dot minus del by L by del by Qj plus del by R by del by Qj is equal to 0. Next example for conservation of energy. Show that total energy of a particle moving in a conservative force field remains constant if the potential energy is not an explicit function of time. Let a particle of mass m be moving in a conservative field of force f. Let r be the position vector of the particle at an instant. Then total energy of this particle is E is equal to T plus V. T is kinetic energy, V is potential energy. Differentiating one with respect to T, we get d by dt is equal to dt by dt plus dv by dt, where the force F is equal to m dv by dt. F dr is equal to m dv by dt plus into dr by dt into dt. F dr is equal to m dv m v dv. F dr is equal to d by dt d of 1 by 2 m v square. F dr is equal to dt. F dr by dt is equal to dt by dt. We have potential energy V is equal to V of RT. Therefore, dV is equal to dou V by dou X dx plus dou V by dou Y dy plus dou V by dou Z dz plus dou V by dou T dt. dV is equal to del V dr plus dou V by dt dt. dV by dt is equal to del V dr by dt plus dou V by dt dot t. Substituting in this, d by dt is equal to f dr by dt plus del v dr by dt plus dou v by dou t. D by dt is equal to f plus del v dr by dt plus dou v by dou t. Since f is conservative, f is equal to minus del v d by dt is equal to minus dv by del by v by del by dt. Now if the potential energy V is the independent of time t, then d by dt is equal to 0. This implies that E is conservative. If the forces acting on a particle is conservative, then the total energy is conserved. Solution proof. If the particle is acted upon the forces, then it moves from position P1 to P2. Hence, the work done is given by W is equal to P1 to P2 F dr, where F is equal to PR dot is equal to M dV by dt. W is equal to integral from R1 to R2 m dV by dt dr by dt dt is equal to R1 to R2 m dV by dt v dt is equal to d by dt of 1 by 2 mv square dt 1 by 2 mv square R1 to R2, that is 1 by 2 mv2 square minus 1 by 2 mv square, that is W is equal to T2 minus T1. Now if the F is conservative, then it is derivable from a scalar potential V, which is a function of potential only. Therefore W is equal to minus R1 to R2 integral from minus R1 to R2 dou V by dou R dr is equal to minus r1 to r2 dv is equal to minus v r1 to r2 and v1 minus v2, and t2 minus t1 is equal to v1 minus v2, and t1 plus v1 is equal to t2 plus v2 is equal to constant, t plus v is equal to constant, and hence this shows that energy of the particle is conserved. Energy of the particle is conserved.